не помните, коли ви входите час на трансляцію, ви забудете. Привіт, включилася. Okay, so I want to start with the overview of the Grothendieck duality. So I want to start with the statement of the Grothendieck duality. So let me assume that I have a map between two schemes. This is a map of schemes. So of course the Grothendieck duality is the topic in the algebraic geometry rather than foundations of algebraic geometry. So I will assume this course that you know a lot about schemes. For example, I don't want to explain what's a proper morphismal scheme, what's a separated morphismal scheme, etc. So to make this statement that I'm going to make in a minute correct, well, I need some assumptions on the f and the x and y, but at the moment it's just some overview, so I won't give any technical details about this triple. So in this situation, well, we have the right functor for the function f with the lowest part. So this is a functor. I need this functor to be a functor from the derived category of x. So this stands for the derived category of x of OX modules with quasi-coherent homology, and it lands also in the same category on y. So there is such a functor, and for this functor also there is a left adjoint. So there is a functor. So this is f upper star. So that's a functor from the derived category y to the derived category. So this is derived push forward and derived pullback, or derived direct image and derived inverse image. So this we have a conjunction. Sorry, the other way around. So I have an adjunction like this, and the Grothendieck works with another adjoint functor. So this is the right adjoint functor to the push forward. So this is notation. Well, notation could be different. Standard notation, if I just think about this as a right adjoint functor f with a cross, but this also can be identified with the f upper shriek under assumption that f is proper. So if f is not proper, then the definition of f upper shriek is a little bit different, but in the proper case they coincide. So let's assume.
What does it mean f with x?
So this is with the cross, right?
Yes.
So this is by definition just the right adjoint to this functor.
Does it always exist?
Under some assumptions on x, y, and f. So for example, it exists, or I can say at the moment that if you assume that this is quasi-compact, quasi-separated, let's do the same as for y. For example, f is proper, it exists.
And by the way, can we construct it явно?
Well, in a sense, this is the goal, right? So if you want an explicit construction for a proper f, well, I don't think this is possible. But if, for example, additionally assume that f is smooth, then it will be just this functor tensor product with the relative polarizing sheaf. So one of the goals of this course at the end is to prove this theorem. But I'm going to use this in the overview, so just wait 4 minutes. Okay, so the problem is that, well, you can notice that this functor that I find on the flow-derived category. I don't assume that this is, for example, bounded on the right and this is bounded on the left. And to do this, well, I need some technique. This is called the K-injective and K-flat resolutions. So this is the other thing that we're going to discuss in this course. Also, for the f, and you can notice that these two functors are derived functors, and the f in the cross or upper strip, this is not a derived functor, this is only defined on the derived category, and usually this is defined only on the D class. Well, it could be extended to the whole-derived category, but it is a little bit complicated. I'm not sure that I'm going to extend this functor to the whole-derived category, but we'll see later in order to discuss this functor.
The class means that it's bounded from below.
Yeah, so it means chronologically bounded. It means that there is a number, and if you
Below and up, or just
no, this means that you can choose a number, and after this number on the left, all the cohomology are trivial. So this is the class. And the same as for the minus, if you can find a number and up at this number and higher, all the cohomology are trivial. Okay, so what's the statement of the Grothendieck duality? So I need to take two complexes. At the moment, to indicate this is complexes, I'm going to put a little dot. So that's a complex of the OX modules with the quasi-coherent cohomology, and there is another complex F that lives on 1. So we have quasi-coherent cohomology. So then the statement of the Grothendieck duality is the following. So I apply push forward to the derived sheaf form between E applied to the complex large F. So this is on the left, and this is quasi-isomorphic to the derived sheaf home between the derived push forward of the E and complex F. So that's the statement of the Grothendieck duality. So you can see that this is, well, essentially, well, let's do the following. What happens if you take this statement, so let me call this maybe star, this quasi-isomorphism. This is quasi-isomorphism. And what happens if I apply H0 with the star? And so this is quasi-isomorphism to complexes of sheaves on X, so this is for everything on the Y. So this is X.
I believe that we get just projective formula. We just get projective formula.
No.
We get third duality.
Well, what we will get, though, if you apply the zeros to homology, so we can build the zeros to homology on the left and on the right. Well, what you will get, you just get underived version. And underived version tells you that the home X between E F upper strip of the F is isomorphic to the home of the Y but this is just a statement that I said in the beginning, that the functor that I consider, well, here I consider Grothendieck duality say for propomorphism, that this functor is just the right adjoint. So applying H0 will just give you more or less the definition. So the point is how you can upgrade this definition to this shapified version. So this requires a little work, but you're right. If when you do this, one of the approaches is just to use the derived projection formula. Okay, and now I want to look at this formula. So maybe at the moment it's not clear why this is such a nice formula. It's an interesting statement, and I want to do several reductions and reduce this statement for more and more elementary statements. And yeah, I suppose you know at least some of these statements. So, for example, let me assume that x and y are regular. Now I can also assume, and I think in this course I'm going to do this, that the field is algebraically closed, and I can say that x and y are smooth varieties over field. And f is smooth. So, in a way, everything is smooth. So then, one of the things that we're going to prove is that there's an explicit formula for the f upper strip. So this is quasi-isomorphic to the derived pullback of the complex. And then we take a tensor product with the relative dualizing shift. Well, the shifted, well, I assume that this omega sub f is just a line bundle. And to get the dualizing object, you need to shift this in the right dimension. So here, omega sub f can be defined easily. So you just take omega on x, then the product with the pullback of the omega of y with the double. And the dimension of f is just by definition kind of the expected dimension of the fiber. So dimension of x minus dimension of y. So in the regular case, there is a formula. Now, additionally, so I continue to assume that everything, well, the x and y are regular, f is smooth, and I additionally assume that y is just a point. So spectrum of some field, call it OK. And maybe even for simplicity, let me take E to be not just a complex, but simply just a sheaf. So E is a sheaf, so quasi-coherent sheaf. So where? So E was on X. And complex F, in this case, we just take to be the field, right? So this makes sense because when Y is just vector of the field, the category of quasi-coherent shifts is just the category of vector spaces over field K. Okay, so let's look what this formula gives us in this special case. So then I'll get on the right hand side, sorry, on the left hand side, R from E. So here I'll get omega x, right? So in this, when y is just a point, the relative omega f is just omega x, and I just need to shift this in the right dimension. So say shifted by d. So here d is dimension of x. So this is shifted by d, and on the right so here we have direct push forward, but if you push forward to the point, this is just the direct functor of the global sections, or just in other words, the functor that computes the cohomology of the sheaf. And okay, well, this is.
Well, you can write it simpler.
Hmm?
You can write it simpler.
We can write what?
The rest part is just RG of E dual.
Yeah, that's right. Well, of course, this is in the y. Y is kind of semi. This category is simple. Everything is projective injective, so there's no really this derived part. So I can as well just erase this. So this is just a dual to the homology. And let me rewrite this. So if I want to move this, okay, maybe I just, not to confuse myself, I just write this. I compute the homology at the level I, so then I'll get here x.
Sorry, I don't understand. Why we remove that?
Well, because this form is over y, right? And y is just a point.
Ah,
So there are no derived factors if you just work in this category. So then you get xi between e and omega sub x shifted by d. So I'm computing i's homology on the left and on the right. And on the right, this will be, so the cohomology with the index minus I think, x, e, and then dual. So this star is just the home into the field key. Right? So this minus y, because this is contravariant functor, this is the duality. So, or in other words, if, well, this x is the same as the x I plus d between e and omega x. And this is isomorphic, so h minus I of the x e dual. And now I just want to change index to get, yeah, so maybe we just simply say that the j is I plus d, right? So, so then the minus I is equal to e.
by the way,
minus
what
j.
is minus I homology?
Well, because this is duality, right? So this is contravariant functor.
Yes, but we use that duality is just a home
Yeah.
from this. Okay, this means that it should be R gamma.
So I'm applying, say, you think about this, I am applying a hi to this thing, right?
Yes.
And if I want to compute the cohomology of this complex, this will be just the dual of the cohomology of this complex.
Oh, okay.
Because this is contravariant functor. Yeah, so the hardest part of this computation is this one. So I denote j, the sum of I plus d, right? So then the minus I is d minus j. Check this, I think this is correct. So in other words, the identity that I get, I'm going to use again, instead of the index j after this computation, again I, so xi between e and omega sub x. So this is isomorphic to the h with the index dimension minus I x e and the dual. And if you learn some algebraic geometry, you probably recognize this formula, right? This is called the Serre duality. So this is Serre duality, and you can see that the Serre duality is a special case when you take this formula that works in the relative situation and assume that the y is just a point, and also assume that you have a smooth morphism, or in other words that y is just the smooth variety over a field key. Okay, so if you don't have questions about this, I'm going to erase this. Okay, maybe there is one more reduction, one more way we can simplify this. If you additionally assume that this E is not just a quasi-coherent shape, but this is a vector bundle. So if E is a vector bundle, so what we can simplify, we can notice that for a vector bundle, we always have the following formula. If I, for example, want to compute x, I can write as well R home, so say xi. I have to quasi-coherent shapes, say f and g. And here I have a tensor product of the first argument with the vector bundle. So you can move this kind of vector bundle from the first argument to the second argument and take the dual of this vector bundle. So this isomorphic to the x I f in dual tensor product with the g. You've probably seen this formula for slide structure. Well, the interesting formula, more general formula, you don't need the assumption that E is a vector bundle. Well, you just say that the tensor product is the left adjoint to the home functor. Right, and in this case, since this is a vector bundle, we can simplify this form to this product again as a vector bundle. No, by the way, notice that this check, so if I want to, so this is definition of the check, this is just the home dual vector bundle, so home into the OX. So then the formula that we get is even simpler. We can say that the instead of that x, I can write. So I can write the x I e omega x simply as the x I omega x e dual tensor omega x. But this x, when the first argument is the structure shift, we can also simplify. We know that this is precisely the ice cohomology, chief cohomology of the object, which we see on the second argument in the x. So then the formula that we get is just without x, just the duality between the cohomology. So h I x e dual tensor is omega x is isomorphic h d minus I x e dual. Just as a simple version of the same duality, and for probably the simplest formula that you usually prove in the complex and complex algebraic geometry is the situation where you take this vector bundle to be the j's exterior power of the omega. Right, so then in this case, you can compute the dual with the omega x, and you'll get the exterior power with the index n minus j. Right. Let's say that here you have j polyvector fields, you have the n form, so you can plug in polyvector field within the form, and you get the form of the j n minus j. So this is how this is done locally on the affine open subset, and then you can take the power by the affine opens and check that everything coincides on the interceptions.
Isn't should be tensor with omega x or vice versa? So you take dual,
Mm-hmm.
and then what do you do?
So this is the dual of this vector bundle.
Mm-hmm.
So this is j polyvector fields.
Mm-hmm.
And the omega, remember that the omega is just the total, the top exterior power,
Yeah.
right? And so if you have the j polyvector field, you have n form, you can plug in this polyvector field in the form, and then you get the form of the degree n minus j.
Mm-hmm. Okay.
So then this formula that we derive give us the following identity between the hi x which is to the power of the omega 1. This is isomorphic to the h d minus I x exterior power of degree n minus j of the omega 1. Okay. So here's the standard formula from the say complex analysis. This is here. This is just a special case. So this is how I want to motivate by the original formula with the functor f aperture. is useful because the other forms of duality just follows from this formula by some quite elementary reductions. Now, I want to finish the introduction and formulate the plan for this course. So I don't want to kind of give the detailed information about the chapters, but I want to say that there will be two parts. So part one in this course. So the plan is to do this maybe till the beginning of November or maybe the middle of November. This will be about triangulated categories. So this is useful not only for the Grothendieck duality, it's useful in many places. For example, you can study representations of solved algebras. Again, derived categories are useful there. You can study commutative algebra and use derived categories. So, and this will be just abstract language. So derived category is always a triangulated category, and this will be the abstract language of just general triangulated categories. Most importantly, what we do in the end of this part, we will discuss compactly generated triangulated categories and prove the Brown representability theorem that guarantees the existence of the right adjoint in quite general situation. So this is how we get the existence of the F with the cross. Well, we just need to prove that the derived category variety is compactly generated, and also we need to show that the push forward preserves the all coproducts. So if you can do this, then we kind of for free get the F upper cross. And in the part two, so we're going to do some algebraic geometry. Meaning that the derived category will be, or the triangulated category will be mostly interested in is just the derived category of OX modules with quasi-coherent cohomology. We'll define derived functors, prove some basic identities between these derived functors, like the projection formula, then derive the Sheffified version of the Grothendieck duality, and prove this formula, that special formula when the morphism is smooth. So this is the minimum that we're going to do. If the time is left, well, we're going to do some other stuff. There's a lot of things that we can do this in the context of the Grothendieck duality. Well, I want to say that the Grothendieck duality is kind of still a topic in progress. Well, there is a, for example, important and a huge paper by Amnon Niemann that is published only last year, for example, that extends this definition of the F upper Schrick to the whole derived category. Right, so this is essential. Well, the preprint existed maybe for 10 years, but the published version of the previous year, so it's a relatively recent result. And there are other stuff. For example, there is an approach. Well, the standard approach for the F upper Schrick is you use Nagata compactification. Right, so you can take a morphism and you can decompose this morphism into. So we have X to the S, some morphism, and you can decompose this into open embedding and the proper map. So this is open embedding, this is proper map. And the existence of such things is called Nagata compactification, and then you derived for this functor F, this F upper Schrick. So here this is proper. You take, so F upper Schrick is, say, this is say U, and this, let's call this F with a bar. So we first apply U, which is just the U with a star, and then you take the composition with the F bar with the cross. So that's the standard definition.
You should change it. So it's from derived category of S to derived category of X, no?
No, this is from the X to the S.
Then you should change U to the lower star. So U upper star is from derived category of X bar to derived category of X.
Yes.
So it shouldn't be true.
Wait, just a second. Yeah. So this is F with the upper Schrick. This is from the S to the X, right?
Yes, so then you should change the
Yes,
order.
I need to change the order. Yes. So this will be
Plastic.
upper star composition. So kind of if you know the definition for the proper of the f with the upper cross, you know that this definition. But this is, of course, as you can see, a terrible definition because it depends on the how you choose compactification. And compactification, of course, is not unique. So there's a huge theorem.
Excuse me, I don't understand. So, we have a morphism from X to S.
Mhm.
And we say that if it's good enough, so there are X.
So then there is another scheme x with a bar.
It's sounds bar.
Yeah, so it exists. It's not unique.
Mhm.
Such that this U is an open embedding, and this is a proper map. So you can see this kind of you can compactify x to the x bar, and you can do this in the relative situation. So this is called Nagata compactification. And recently, again, just last year, appeared a work where you can define this f upper star using some formulas from the Hochschild homology of schemes without using this Nagata compactification. So maybe if time permits, at the very end of this course, I'll try to develop the theory of the f upper shriek without using Nagata compactification. So I'm studying this paper right now, so I hope that by the beginning of the December, I understand this. So that's the plan for the course, well, just a rough plan. Now, another thing that how you get the mark for this course, well, there will be 4 assignments. Well, meaning that I'm going to give you, if you took my courses before, you probably know what I'm talking about. So I'm going to give you just a list of problems. For example, I know, here I don't know too many problems, so probably there will be at least maybe over 10 problems, maybe sometimes 11 or 12. But in any of such problem list, you just need to solve 10 problems. So if you solve 40 problems per semester, that's 100%. And usually for each assignment, there will be 2 weeks. So this is how you can get a grade. What else what I want to say in the beginning? Maybe also books and papers that I recommend. Well, for the first part about triangulated categories, there is a book by Amnon Niemann, which is just called Triangulated Categories. So probably everything that I want to say about triangulated, well, not really, but almost everything that I want to say about triangulated categories will be in this book. And of course, there is much more in this book. This is almost 500 pages. So this is for the first part. For the second part, there are several sources. So first by Lippmann. This is where he introduced this notation with the f with the cross, and after that work, everything in this area used this notation f with the cross. So it became standard after this work and this work from 2009. So it's called something like the derived, I think the derived functors and duality. So this is kind of short book or a long paper. This 250 pages. It is published in the lecture note in mathematics with another text about something diagrammatic, or I'm not sure. So I think there is a volume in the lecture notes in mathematics where the first part is just this independent text of Lippmann, and there is a second part, Hashimoto, I'm not sure about the equivariant case or the diagrammatic case when you have diagrams or schemes. Well, this part will be important for this course. And also, I think that you can find this on the author's webpage for free.
It's got notes on derived functors and Grothendieck duality.
Okay, no, I almost guessed it. Okay, so but I want to say I don't want to follow this too much. So just another good reference. But in this course, I don't want to use it too much. I want to use another 2 sources. Also, well, actually, I think most of the time I'm going to use papers, not books. There are several papers by Niemann that I'm going to use. There are other papers, and if you want books, I can recommend another one. So this is just a textbook, recent textbook in algebraic geometry. So this is just, well, 2 volumes in algebraic geometry. We will need volume 2. And this volume 2, there is chapter 25 about the duality. So it's nicely written chapter. There are a lot of information there. And as a general, if you want a textbook in algebraic geometry, this might be one of the best options. This is relatively recent, so the volume 2 was only published again last year, in the autumn and the fall of the last year. And contains a lot of other information, not just duality. So the first volume is something like 700 pages, the second volume is 800 pages, so you can see this is 1,500 pages on algebraic geometry. If you compare this, for example, with the Hirschhorn, well, the Hirschhorn is just 1/3 of that. So it has a lot of details, and chapter 25 will be useful. And also chapters 21 and 22 about the OX modules, derived categories for OX modules, and derived categories with quasi-coherent homology. Okay, and another thing that you can look is the Daniel Murphy, which was a student of Amnon Niemann, has some notes on the triangulated categories and derived categories on his homepage. That is also quite useful. Well, unfortunately, these notes were not exactly correct. There are some mistakes here and there, so we need to be accurate when we read these notes. But it has a lot of material, a lot of kind of slow explanations with the details. Okay, that's all I want to recommend. And maybe for some particular topics, I can recommend you just a paper if you're interested.
Yeah, I want to ask about this side of writing. T equal to n, yeah?
Yeah. This is just the dimensions. Okay. So that's all about the information and the structure of the course.
Yeah, and the course will be like the first one is the lecture, and the second is the seminar.
No, we'll lecture and lecture most of the time. Maybe I'll do a seminar maybe once or twice, but at the moment I don't have any plan to do seminars.
Okay.
So instead of seminars, we get these problem sets that we need to solve. Okay, so let's start with the chapter 1, where we cover some basic definitions of triangulated categories. So let me call this triangulated categories. And triangulated functors. So when we start with the definition of triangulated category, well, that's already something not trivial. So let's say this 1.1 definition. Yeah, and there is this kind of standard way to write this. Instead of writing over time triangulated category, we're going to use triangle, not triangulated for shortness. So definition and some remarks about this definition. So let T be an additive category. So the structure of the triangulated category T, so it's being triangulated category is having additional structure. So is the following. So given by, so the structure of G is given by, well, first we have a functor that I'm going to call T from the category. The same category, so this kind of out equivalence of the category. So this is additive equivalence. So in our examples, well, maybe before I finish the definition, I want to say what's the idea. If you haven't seen triangulated categories before, the idea is, well, you do homological algebra, and homological algebra, you work with resolutions. Right? Resolution is a complex, and you can prove that, for example, if you take, say, a module, take two resolutions, and these two resolutions, well, at least they quasi-isomorphic. You can say more, but at least they quasi-isomorphic. So then the idea is, instead of studying just resolutions, to study all the complexes of the quasi-isomorphism. And this is formally called the derived category. And if you want to do some homological algebra, you need the notion of exactness. For example, in a given category of short exact sequences, you can say about left derived functors, right derived functors, short exact sequence, one applied derived functor, get long exact sequence of derived functors. Here, this instead of the short exact sequences, we will consider this additional structure, which gives the triangulated category structure. So the point is that if you consider all complexes up to quasi-isomorphism, it's not an abelian category, but this is now a triangulated category. So it's canonically have this structure that I'm going to define right now. So the first part of the structure is this shift, this functor T, and if you in the standard homology context, when you study complexes of sheaves or modules, then this will be just the shifting of the complex by one position on the left or on the right. Doesn't really matter. So for this reason, sometimes I'm going to call this T just the shift factor. But abstractly, this is just some additive equivalence of a category. So this is the first part of the data, and the second part of the data is a set of distinguished triangles. So for shortness for distinguished triangle, because we're going to use this a lot, I'm going to just write DT, distinguished triangle. So what's the distinguished triangle? Well, this is just three objects, A, B, and C in the category. And we have also three maps, F, G, and H. So a triangle is just kind of this information about these six objects. These six things, three objects and three maps. So this is called the triangle because you can organize it as follows. For example, you have A, B, and then C, right? And then you have these maps, F, G, and this H. This kind of maps to the A, but it increases and the shift this object by one position. So absolutely just apply factor T. But I don't think that this picture is really important for understanding triangulated categories. So there's a set, or maybe even a class. Let me say this is a class. Class of distinguished triangles. Okay, so before I continue and formulate the axioms, which this class of distinguished triangles is satisfying, I want to introduce notation. So I'm going to say that I have an object A shifted by 1. This is by definition is the result of applying T to A. As I said, in the derived categories, this is what really is. It's just a shift of a complex in one position, say to the left. And of course, we can generalize this to from 1 to any integer just by iterating t or t to the minus 1, when t is invertible, result is equivalence. So this n is an integer. So this is a topic of notation. And also, to formulate the axioms and talk about them, I need to say what the morphism of distinguished triangles is. So, morphism of distinguished triangles. Now, that's a kind of what you expect it to be. If you have two distinguished triangles, yeah, by the way, in the notation, I'm also going to use the same notation for the maps. If I write a map shifted by 1, this is by definition t applied to this map. And you can, of course, extend this definition to any integer. So you have two distinguished triangles. So then the map between them is these three maps between the objects, phi, theta, and theta. So on the shift, you just take the shift of the phi. And of course, all the squares that you see here are commutative squares. So very straightforward definition of a morphism. Okay. So now we have axioms. So the data satisfies the axioms. So there are 5 axioms. So starting with the 0 axiom, TR0. So it has 2 statements and both of them are quite trivial. So a triangle isomorphic to a distinguished triangle is a distinguished triangle. So since we have a notion of a morphism between distinguished triangles, well, actually you can define this for any triangle. Triangle is just 3 objects and 3 maps. So if you have such 3 objects and 3 maps, and there is isomorphism, so phi, psi, and theta are isomorphisms to a distinguished triangle, then this first triangle is also distinguished. Well, it's kind of tautological axiom. And also I want to put in TR0 another tautological axiom that says that triangle we have some any object, and then we have the identity map from this object to itself, and then we have a 0 object, and A shifted by 1. So this is a distinguished triangle. Okay. So for any object, this thing is distinguished triangle. Okay. Next axiom, TR1. It says that any map F, say between objects A and B, can be extended to a distinguished triangle or completed. So can be completed to a distinguished triangle. So we have A, B, some C, and A shifted by 1, so F. And there are some other maps, G and H. So, essentially saying that, well, in the axiom, I only say that this C exists. But it's not a hard exercise when you have the whole list of axioms to show that this C is unique up to isomorphism. So essentially, up to isomorphism, any triangle is defined by just the first map in the triangle. Okay, so in the TR2, well, this axiom has a special name. Sometimes this is called the rotation axiom. And it says the following. So you have a triangle suppose A, B, C, A will shift by 1. So with the maps F and G and H. So this is distinguished if and only if and the shift to the right of this triangle is distinguished. So we have B map G to the C, then map H to the A shifted by 1, and then just by definition we put the additional minus, so we have F shifted by 1 but with a minus will be shifted by 1. So we can rotate the distinguished triangle and still get a distinguished triangle.
And why
No-
is minus?
Hmm?
Why F?
Really, this is just a convention. You can do the theory without this minus, but it means that you get additional minuses in other formulas. And in practice, it's easier to put minus once here.
Usually when we take column or something like this.
Yeah. So in the example, when you take, say, derived category or some Abelian category, that's a generate category, this, for example, TR1 works as follows. You have two complexes, you have a map between complexes, and this is just the column of this complex. So by convention, I put minus here. But there are, of course, many texts in generate categories, and some texts you don't see this minus. Okay. And notice that this is if and only if statement. That's important because it means that you can rotate to the right or you can rotate to the left. So rotations are possible in both directions, and with this rotation axiom you can see that really this triangle is kind of this, it can be infinitely continued to the left and to the right. So this kind of string of data, not just the three objects. Okay, so TR3. Again, suppose you have two distinguished triangles. And almost the map. So you have in the map you have only two maps. So say this is phi, say this is phi. Well, so this is distinguished triangle and this is distinguished triangle. So when you have two distinguished triangles and maps phi and psi such that this square is of course commutative. So this is commutative. So then there is a map such that these three maps form a map of two distinguished triangles. So in some sense this is like axiom TR1 but for morphisms. So that 2 out of 3 completely determines. And you can see that because of this rotation axiom, again, you can always say that 2 out of 3 determines everything. If you have, say, this is 3 morphisms, if you have 2 objects, then the third object is determined. If you have a morphism of triangles, any 2 morphisms, I can write it here, I can write it here, I can write it here, because after rotation, I can always do it back here. So if you have 2 components of the morphism, the third component is determined. It exists. And well, it's not canonical, but after isomorphism it is. Really. Okay. Well, maybe before I continue with the last axiom, I can squeeze in an exercise, which is simple, but if you haven't done this before, haven't seen this before, that's a good exercise, which is really one-line computation that proves it. It says that if you have a distinguished triangle, so A, B, C, and A shifted by 1, maps F and G and H. So this is a distinguished triangle. Then the composition of the any 2 maps, but since we have rotation axiom, I can just write this for the 2 maps. So the composition G and F is 0. This follows from previous 3 axioms. Okay. So axiom, the last one, TR4, also known as the octahedral axiom. Which is the most interesting and non-trivial. Okay. Suppose there are three distinguished triangles, and notation now is very important, so just copy my notation from the notes, otherwise I'll get plenty of mistakes. So I'm going to call the first triangle objects A, B, and C prime, and the maps will be U, J, and some partial del. So the next one is the B map is V to the object C. So the second map I'm going to call X to the A prime, and the last map is I to the B shifted by 1. And the third triangle is for the composition of the V and U. So A and C, and the map here is the composition of the V and U. And there is another map Y from the C to the B prime, and the map delta to the A shifted by 1. So this is we are given. But you can notice that really what we are given here is just two maps U and V, right? Because if you have two maps U and V, we can continue this to a distinguished triangle, continue this to a distinguished triangle, take a composition, and also complete this to a distinguished triangle. So really we are given two maps. But I introduce notation for all the information that I have. So then there is fourth distinguished triangle, C prime, some map F, B prime, some map G, A prime. So the last map is the composition of the J shifted by 1, composition with the I to the C shifted by 1. So there is this another distinguished triangle well, such that in the octahedron that I'm going to draw here, it's a little bit complicated since it's octahedron. So I have A prime, C prime. So then there is C map X. There is A. So this is composition of the V and U. So this is del. And there is B. There is B prime. And all the maps that I have on these distinguished triangles. So this is V. This is I. It would be nice if you could check my diagram, all the arrows are correct and the directions of the arrows are correct. So you have this kind of way of organizing the data, and so this octahedron you have faces, right? You have 8 faces, and the claim is that out of these 8 faces, 4 faces are distinguished triangles. So 3 are given, and the last one requiring this axiom. So together therefore 4 distinguished triangles. So let me say this is condition 1 for the octahedron. So the 4 distinguished triangles form 4 of the faces. 2 other 4 faces are commutative squares. Then there is condition 3, which you don't see on this diagram, but it says that if you consider composition of the map Y and the map V, then this is the same as the composition of the F and G. And condition 4, if you make a composition of the U shifted by 1 composition with the delta, this is the same as the composition of the I and G.
Can you write pluses or something where is shifted? What? To the shifted.
Well, you need to find it. So it's
Like delta I.
so this first one from the C prime to the A. Well, I don't want to put 1 here, so I'm going to write this just plus 1 here. So then I also has a plus 1. So I is here. This is plus 1. This is here. Plus 1. And finally, well, the last one will be complicated because it's the composition of the 2 maps.
Yeah.
So maybe how I do this. Well, that's the original form in which this axiom was formulated. This is why it is called octahedral axiom. And I only wanted to show this axiom for historical reasons. Yet really, when you work with the triangular categories, you don't draw this octahedron and try to find some information in this octahedron. So this diagram can be organized at least in the other 2 ways, and you get some planar diagram or this 3D diagram. And this is what I'm going to do next. Yeah, and by the way, before I do this, maybe I squeeze it here. What's the intuitive meaning of this octahedral axiom? Well, this is the triangulated analog of the statement that you have the following short exact sequence. So in the algebra, for example, when you work with the modules, we call this something like third isomorphism theorem. And the octahedral axiom is just a version of this isomorphism theorem, but for triangulated categories. And because really, we can think about this kind of not well, naively, it's not exactly correct, but this C, the cone that you have when you start with the morphemes, this is something like a quotient. So C prime is something like a quotient of the B mod A prime is a quotient of the C mod B, right? And then the B prime is the quotient for the composition, and then the existence of this fourth distinguished triangle is more or less like this statement, analogous to the statement, if you think about these cones as analogs of the quotients. So that's the intuitive meaning of this, but you can see that's not enough because they also have some additional requirements, 3 and 4. And if you drop this, well, you get just significantly weaker axiom that doesn't work in the applications. Okay, let me restate this octahedral axiom in 2 other ways that we're going to use in this course. So there will be 2 diagrams. So the first one is the following. This will be a 4x4 diagram. So we're given kind of 3 triangles, we can construct 1 more, and everything can be organized into the diagram. Okay. So the exercise is to check that you have 4 distinguished triangles and 4 another commutative squares, and you can find, and also have conditions 3 and 4, and you can find this, that when all the squares here are commutative, then you have the same information, the same kind of commutativity, except you don't have 4. So the axiom is commutativity of this diagram, where you have 4 distinguished triangles. Well, you can see these distinguished triangles, right? For example, this is the first one, this is the second one, this is the third one, and the last one, this is with the F. So where is F? So this is the last one. So this thing plus condition 4. For example, you can notice that the commutativity of this square is precisely condition 3 in the previous formulation. Okay? So 4 doesn't follow from this diagram. Additionally, you require this 4. So this is one of the ways to state after axiom in the useful form. This is how we're going to use this when we prove something.
So this diagram only require all the squares to commute. This diagram all the squares commute.
Yes, yes.
That's because we formulated the rotational axiom differently. We don't have the anti-commutants we are usually having the other.
Yes. Yeah, so this is one way, and there is another way, which is a little bit more complicated, but you don't need to require axiom 4 additionally. And depending on what you're proving, one formulation or another of this axiom will be more or less useful. Again, this will be a 4x4 diagram. The first distinguished triangle is kind of hidden here. You roll like this, but since this is the identity, you can obviously see. So in particular, we can see that the commutativity of this square is condition 3, and commutativity of this square is condition 4 in the first statement of the axiom.
And what about the other columns?
Well, you can locate, as before, 3 distinguished triangles. So this is distinguished triangle, this is distinguished triangle, and this is distinguished triangle, which are given, right?
Not this.
No.
This to the H. E, C, no, that's not.
Yeah, so this is distinguished, right?
Yeah.
This is distinguished.
Suppose, yeah.
This is distinguished, and also this is distinguished. Or this is not. No.
No, I don't speak about row, I speak about columns.
In the columns, we only have kind of this, the fourth one.
And the other column,
Of course not, no. They're not distinguished.
I saw. Because in this diagram, all columns and all rows are.
But the kind of trivial one, right? So this is kind of trivial information. So the second exercise is to check that what you see here with this four distinguished triangles and commutativity of all other squares, this is equivalent to the original heteroaxiom or the previous statement of that heteroaxiom. Well, just an exercise in looking at the diagram and finding that all the commutative squares are the same. Okay. Okay, so this is the end. So we defined the notion of triangulate category. As you can see, this is kind of complicated. But I want to say about this after heteroaxiom, because here we're going to develop some foundations for triangulate category. We're going to use this axiom several times, no, maybe half a dozen times. But if you don't work on the foundations of triangulate categories, in most cases you don't need this axiom. The first from 0 to the first four is enough. For example, there is even a textbook on the Fourier-Mukai functors in algebraic geometry by Daniel Huybrechts. And there he just doesn't bother formulating this last axiom, just formulate the first four, and that's enough for his book. And there are a lot of theorems and then very interesting geometrical theorems. Okay, so let me introduce the notion of the
We will
homology.
need this action, yes.
Hmm?
But we will need this action.
Yeah, we will need it, maybe even today. So there are some statements that for the proof we need this axiom. Okay, so another definition.
Is it true that there is no examples of the categories where all axioms but the last hold?
Yeah, I believe this is true, yes. There was actually even the conjecture that the TR4 follows on previous axioms, but as far as I know, there are no proofs of that. Okay, so definition. So let T be a triangulate category. And also we take an abelian category, so A is an abelian category. The functor, say H, from the triangulate category to the abelian category is called homological. If for every distinguished triangle ABC maps are F, G, and H as before, the sequence in the abelian category. So we can talk about exactness. So the sequence functor H applied to A, functor H applied to the map F, functor H applied to the B, and functor H applied to the G is exact in A.
Can I ask one question about this?
Hmm?
Pavlov theorem. So we assume if all these squares commute and the three rows are distinguished triangle, then there is another distinguished triangle.
Exactly,
In the
yes.
fourth row.
Well, actually, no. If we assume that we have three distinguished triangles, so we kind of have the part of this diagram, right? So only with the three distinguished triangles. So we have this, and this.
Yeah.
Right? So then you can kind of complete this to the whole diagram.
Yeah.
In such a way that this is distinguished triangles and all the squares are commutative, all the new squares are commutative.
Mm-hmm.
You require function to be additive.
Yes, of course, yes. so say an additive functor. Additive functor is homological if we have this. So actually we can require the exactness at this position, right? But since we have the rotation axiom, actually what we have in this definition is this infinite sequence, infinite exact sequence. So you can continue this to the right and to the left, right? So maybe I formulate this as a remark. So remark. So by rotation axiom TR2, the sequence, the infinite sequence, so we have H applied to the C shifted by -1, then the H applied to the map little h shifted by -1. This is to the H applied to the A, H applied to the F. All the rest is as usual. In fact, we have this infinite on the both sides, exact sequence in the abelian category. Well, maybe this is a kind of definition with the prime, so I want to define the homological functor. I can repeat the definition of the homological functor in exactly the same way. I just require this functor to be contravariant. But I can also say the following. So if, another way to formulate the same definition, if T is triangulated, so then opposite category is also triangulated category. Well, you can check this. That's a simple exercise. Well, the only thing you probably need to notice in this exercise is that if you look at the shift functor, so I'm returning to my basic notation with the T, so T stands for the shift functor in the opposite category, then this will be T to the -1 in the original category. So then the cohomological functor okay, maybe I again denote this by H. So this will be a functor from the opposite category to the well is homological functor from the opposite category. Or you can just take this definition and put opposite here, and in this diagram put the arrows in the other direction.
What do you see here? T.
Well, if you go to the opposite category, then the shift functor in the opposite category is the inverse of the shift functor in the given category. So the main example of the homological and homological functor is the following. And I'm going to formulate this as a proposition. So let yeah, thank you. Actually, it's time for a break, right? It's time for a break, right?
Yeah.
Okay, make a this proposition.
Если у нас нет, размер появится, у него определенная сегодня будет, ну там, все контексты будут заложены своим технологией. Это значит, что если вот там будет гармоническая размерность 2, то у нас все контексты могут иметь вид либо, что у них стоит в технологии там через промежуток. Вот, потому что если мы возьмем вот эти две, вот обрежем, возьмем вот эти две космологии, как бы вот обрежем, вот это вот все назовем там его космологию возьмем там H, I, там вложим и отобразимся потом вот сюда, то есть там H, I, 2. Ну там H, I, 2, ну, и здесь плюс 2, ну и здесь стрик еще нормально. Вот, тогда вот здесь у нас должно настраиваться логарифм H, I на единицу. Сейчас, ну здесь минус 2, да, наверное? Ну и там вот это, короче, x вторые. Вот. Их не может быть. Значит, А должно быть просто суммой этих третий, да. Их нет, значит, А должно быть просто суммой этих космологий. То есть тут либо вот так стоят космологии, либо по две пары. А здесь ничего не может. Ну, соответственно, там дальше тоже так же можно там на всяких примерах про многообразие, там либо они по 3 стоят,
Ну да.
либо
Ну, как бы
один.
как бы обязательно,
Ну да.
если есть молодые
Мне в этом семестре сложно план создавать, только руководить, а посмотреть.
Кстати, мне кажется, камень
Да, вот вы говорите, что там у Губерца нету теоремы Артальда. Ну это, конечно, хорошо, но он и теоремы не доказывает некоторые. У него есть 8 Grothendieck, там в третьей главе. Ну, а вот теоремы Артальда нету долго.
Не, ну там четко там наказывают какие-то всякие теоремы.
Не, ну какие-то там Орлова, да, доказывает теорему Орлова, там теорему Орлова. Не, он много геометрических теорем доказывает, там действительно круто, но просто там иногда это, иногда он доказывает, там используется что-то, что и не знаю.
Ну, ты тогда не стимулируешь, если еще такие проблемы.
Ну да. А он их использует.
А насколько самолюбие будет переноситься на более общее операционное пространство, как логическое? Во-первых, есть целиком, а вот насколько будет трудно заполнить вторую часть на логическое пространство?
То есть это будет подтвердить.
Да нет, поскольку не знаю, что в везде, поэтому будет собрать.
Я думаю, что 99%. Ну, нет, я сейчас не знаю, вот это утверждение, какая у вас будет основная производная категория. У вас будет производная категория пучков, абелевых групп, но у вас как раз конструктивные космологии, правильно?
Нет, а там же для логического пространства абелевых групп там апер-шрифт, он просто там даже определяется, в понимании есть определение верхнего шага.
Не, ну он же будет сопряженный, сопряженный кэп с нижним шлифом, который много снопов носительный, который может снопов носительный. То есть там все есть кино как это.
Да, то есть это разные.
Но когда вы видите, не идет сложнее, там не так хорошо все работает. То есть если формализм 200 функций, да, он будет психологии нормально, то есть.
Не, вот там верхний шаг тоже определяется только для производных категорий. Он для просто...
Да, но стремление все равно будет сопряжен.
Да.
То есть у вас будет как бы L предельно, он F снизу, немножечко F сверху, немножечко F снизу, понимаешь, но сверху передачка. То есть полный формализм 6 функций. Вот в греческой геометрии такого нет.
А
у Шольца какие-то записки есть по общей формулировке. Там он логин тоже.
Это то, что я планирую читать, но я не читал.
Там какие-то сразу вот эти странички с категориями, так, команды.
Этот курс мы ждем в следующем году.
Нет, там, кстати, в быстром суде прям, может, сколько, может, 14 страничек.
Ну вот тоже с первым раз мне показали одно из десертов. Такое может быть просто полагается известно.
Извините, а можно вот меня в рассылку естественно,
Напишите мне письмо, что
у вас какая вообще? Просто, а Павлов,
I wasn't present as well, but there is recording.
либо Ани, либо Антоний.
Yeah,
я
I
понял.
wasn't going
Я
to
Саша Павлов, очень боялся.
street.
Хорошо.
Street.
Я понял.
You see?
Что, будем сначала просто первым же логину, да?
Ну, не там лучше, что такое сделал,
Ну да. Ну вообще, сайт немного другой.
он, кстати, морально делает правильнее про себя. То, что я не сделал, проблема в том, что вся вот если корпус литературы, то там верно сегодня,
Они правильно.
я такое ощущение, в какой-то момент доказывает утверждение, не помню документа, что если у вас вот есть аксиома смысла мира, потом у вас получается коммутативно диаграмма 4 на 4, я не помню, какая первая, вторая, но там все коммутативно, там что получается какой-то квадрат типа легкой посередине, что геометрически проще, да, почти до карты. И я этого не требовал. Я вот такой случай однажды и вопрос. Мне кажется, что именно чуть-чуть сильнее, не просто точно квадрат,
Ну да.
относительно квадрат, а именно почти до карты.
Но это, как говорится, это, так сказать, это сильнее в случае, если мы найдем что-нибудь, что в нем уже порядке. Это как вот добавление теоремы октаэдра, ну, там, сильнее, чем не добавление. Но мы просто не знаем, как бы, если что-то, где это не работает.
Могут всегда практически точно. Потому что чисто формально для рассматривания чуть-чуть сильнее.
Какие-нибудь, что можно почитать, у меня там блавки многообразные, я беру как бы джезбэк и пушфор. Все работает на ограниченных производных категориях где пушфор. Из-за этого пушфор становится квазикогерентным. И вот пушфор, ну вот он переводит к когерентному, почему-то когерентный, там вот там тексте квазикогерентный. Ну, вот. Проблема в том, что вот квазикогерентный носитель никакой хороший. Вот если что-нибудь, что там можно сделать с этим носителем, что-то сказать, что на самом деле он там более-менее нормальный, что-то такое. Или вот, если какие-то темы взять. Я хочу, чтобы он был занят, или хотя бы какой-нибудь там.
Надо придумать, как еще звать. Вот нужно было давно посмотреть.
Ну там могут у вас готовы соображения.
Произведение. То есть это произведение, ну там гладких собственных многообразий, да, правильно.
Может быть, важно дело, что это правительство определяет хорошим искусством, которое не просто классик, это там меньше смысла.
Ну, а вот такое это написано, что при хороших выражениях уж форвард все-таки немного хороший. А собственно сказать, что собственно, она не гладкая. Да.
Может быть, два многообразия проективных.
Нет, если два многообразия проективны, то если проективны, там это вообще не квазикогерентно, это отображение из когерентных в когерентных. Если они проективны, то там все хорошо. А проблема в том, что это не проективно.
Ну, можно попробовать, я знаю, только посмотреть эти самые космологические, собственно, отражения могут закон. Сейчас не знаю, что космологические собственные. Попробовать можно, если уж не класс космологический собственный, и его сохраняет псевдокогерентно. Могут у вас там будет псевдокогерентно, или не сочетывается.
Что такое космологическое собственное?
Книжку эту скачайте, Павлов.
Это ладно.
Я скинул уже.
Куда?
Мне показали даже на учебнике по семейным, что очень интересный там мальчик, он философ, он прочитал, что ему нужно, конечно, подскочить категории, и но вот он нашел этот учебник.
Где это?
Ну, в совете, да.
Не, именно какая часть?
Ну, просто вы смотрите, где там псевдокогерентные и космологические собственные. Мне кажется, как раз 25 главе есть нет псевдокогерент, по-моему, 23 главе. Ну, там по индексу посмотрели, и все можно направить.
Окей.
Я не знаю, как это работает. Просто...
Не, интересно, я сейчас псевдокогерентный первый раз слышу, поэтому думал, что там найдется.
Okay, so we continue, and I want to show the two examples of the homological factors. So that is the proposition. So let T be well, actually I can say that this is a pre-triangulated category. So pre-triangulated means just I don't require octahedral axiom. So when in the statement I say that the category is pre-triangulated, it means that in the proof I don't need octahedral axiom. So pre-triangulated, then this means that I have TR0 to TR3 without octahedral axiom. So if I have a pre-triangulated category, then the functor, then the main representable functor on where it is the first object, so that's a covariant functor from the triangulated category to the abelian category, which is just the category of abelian roots. So this is homological. So this AB just stands for the category of abelian groups. Representable factor is homological. Okay, proof. So let's take a distinguished triangle. A, B, C. A shifted by 1. Maps F, G, H. So this is a distinguished triangle. So I want to prove the exactness of this sequence, so at the position B. So suppose that we have a map phi from U to the B. Well, in other words, I just work with the elements. So I take element in the H of B, well, such that it is mapped to the 0 by the map H of G, right? So such that the composition U, phi, B, G is trivial. Right? I want to show that this map is actually coming from some map from the U to the A by a composition with the map F. Well, I look at the following. I have a distinguished triangle where we have blue, and the identity between blue, so then 0. And U should be 1. So, and I have a distinguished triangle A, B, C. Okay, so here we have map F from the U to the B, and this map from B to the C, this is G, right? But I know that the composition, sorry, this is not F, this is phi. Right, so I know that the composition of the phi in G is 0. It means that I can draw another map of just this 0 map. Of course, this is factor of this is the map of the 0 object, so there's only one map. So this square is commutative. Hence, by using the axiom GRB, I can say that there is a map here, so call this psi, and this A to B is called F. So that's exactly the exactness, right? So this is the end of it. Well, in other propositions, or proposition with the prime, under the same assumptions, if you look at the functor home where you fix the second argument, and this is a contravariant functor, again to the same category of abelian groups, this is cohomology. We can make a formal argument by going to the opposite category, so you can just repeat the proof. Both is very easy. So these are examples of homological and cohomological functors. So next proposition, I'm going to call this the 5 lemma for triangulate categories. It's not exactly 5 lemma because we only have 3 objects, but kind of special case that works for triangulate categories. 5 lemma for triangulate categories. So if in a morphism of distinguished triangles, let me draw this morphism and triangles. So ABC, ABC with the primes, so and we have maps. I'm going to call this F and G because it's easier than the Greek letters, and I don't need maps in the ABC. So if in this morphism F and G are isomorphisms, then H is an isomorphism. So I formulated this for H, but you can imagine that I can do a rotation. I can as well formulate the statements if the F and H are isomorphisms, then the G is isomorphism. That looks a little bit more like a 5 lemma. Okay, for the proof, I need a diagram which I obtain if I take this diagram and apply the home from the C prime. So let me say that we apply home from C prime to the diagram in this statement, so to the diagram which I call star. And then we will reduce everything to the 5 lemma in the category of abelian groups. We'll get home C prime A, home C prime B, home C prime C, so I have the same diagram with the terms of the second argument. And then there are, of course, maps induced. So, for example, when I write f with a low star, this is by definition means on the first argument is C prime, and the second argument, this is a map, just the composition is. And the same for other maps that you see on the diagram.
So this should be C. Under the H prime should be C. Home from C prime to C prime. H star, H lower star. Yes.
Okay. So what we can see is that we have a lot of, in this way I organize this, we know that since F and G are isomorphisms, of course the induced maps are also isomorphisms, right? So this is isomorphisms. If we shift the map, right, we apply now the equivalence. If we F was an isomorphism, that F shifted by 1 is also an isomorphism. Well, it's actually true for any function, if apply function to an isomorphism, this is an isomorphism. So that's an isomorphism, that's an isomorphism. And then we have the five lemma in the abelian category of abelian groups. So we can say that by lemma in the category of abelian groups, H all star is an isomorphism, which means, for example, that there is a map, I'm going to call this map Y, from the C prime to the C, such that if I apply H lower star to this element, well, get the identity from C prime to the C prime. But such applications of course just the composition to the map H. If I take composition of the H and phi, then this will be the identity of the C prime. Which means exactly that the map H is invertible on the right. Right? And you can do the same argument, but instead you apply functor on C prime, where you put C prime on the second position. Right? So there is a map psi in the other direction, from C to the C prime, such that psi composition is H is identity of the C. But if the map is invertible on the right and invertible on the left, then this phi is equal to the psi, right? It's just a standard computation from the first semester of algebra, right? You just write that psi is the same as psi composition with 1, and you write this as a psi composition with H, composition with phi, with associativity, and conclude this is one composition with phi, which is phi. So H is invertible. It's an isomorphism. Okay, so let me, with this simple observation, the five lemma, finish this first section and go to the section 1.2, triangulated functors. So definition. So let T and T prime be triangulated categories. So formally speaking, let me do formal in the definition, but later I won't talk about this formally. So formally speaking, a triangulated functor is a pair where we have a functor f. So pair f, which is a functor from t to the t prime. So additive functor. And the second element in the pair is natural equivalence. So natural equivalence, I'm going to call this phi from the composition of the F and the shift in the category T to the composition of the shift in the category T prime and the functor F. So in other words, functor F commutes with a shift, and this commutation relation is given by some equivalence relation phi. So triangulated functor is a pair. So if you combine these together, then you'll get a pair of the F and phi. So this pair. But also, of course, we want this to respect the whole structure of triangulated category, not just the shift functor. So we also require that the distinguished triangle is mapped to a distinguished triangle. So such that if A, B, C, A shifted by 1 is a distinguished triangle in T, then when you apply this functor F, you'll get the distinguished triangle in T prime. And here, since we have this first requirement, I can actually write F of A shifted by 1. Right? I use that this is equivalent, is isomorphic to the F of A shifted by 1. So this is distinguished triangle in T prime. Well, there is a kind of trivial remark after the definition that composition of triangulated functors is a triangulated functor, and the identity functor is triangulated. Well, this is just a formal definition, but really in the applications, when I say triangulated functor, I just mean the functor that can be used with a shift and maps distinguished triangles to distinguished triangles. Also, since we think about this triangulated structure as some kind of exactness structure on the additive category, we can also, so say this is remark 2, we can also call this such functors exact. So triangulated functors are also called exact functors between triangulated categories. Just another terminology which is equivalent to the given. Okay, so and another definition. So suppose we have two triangulated functors. So let's take a pair of the F and phi and pair of the G and psi. So these are triangulated functors between two triangulated categories. Well, we also, so kind of in the triangulated work, we have the notion of triangulated category, triangulated functor, and we also need the notion of triangulated natural transformation. So triangulated natural transformations are usually called trinatural transformations.
So there should be not phi.
Sorry, it's supposed to be psi. Okay. So try natural transformation. So let's call this eta from one pair, which is triangulated functor, to another pair. So is a natural transformation additive functors. So natural transformation of additive functors, so beta from F to the G, such that for any object X in the translate category T, the following diagram values. So the functor F, applying this to the X shifted by 1. Then the component phi sub X for the natural transformation. So the same for the second function G. So this diagram is okay. So triangulated functors have one important property, which is the next proposition. So let F be an exact functor triangulated functor. Maybe I stick with my notation. B.
You just write to code that exact functors.
Yeah, but I want to continue use notation that I introduced first. Yeah, so this is, and there is also a shorter way to write this, just triangle functor. Right, so let F be a triangulated functor. And if this triangulated functor has a right adjoint, I'm going to call this H. So then H is also triangulated functor. So adjoint to triangulated functor is triangulated functor. I formulated this for the right adjoint, but for the left adjoint, the same proof and the same statement works. So let me end this. If G is the left adjoint to the F, then G is also triangulated. That's enough to prove only one of the statements. Okay, so proof. So I want to show first of all that this commutes with the shift. So for this I do the string of computations. So I start with the home from some object A to the H of the T prime. Well, let me use notation that in the category T the shift functor is T, and the category T prime the shift functor is T prime. So I think it will be easier to understand if I use notation T, not just the shift by one. So I start with this home. So then by adjunction, so H is the right adjoint, I can say that this is naturally isomorphic to the home F of A T prime of B, right? And then I want to also move this T prime, but T prime is autoequivalence, and it means that also has right and left adjoint, and they coincide, and this is just T prime to the -1. So inverse of this function. So this is naturally isomorphic to the home T prime to the -1 applied to the F of A B. So now, since I know that the F is triangulated functor, the first argument in the home I can just replace by the f applied to the t to the minus 1 applied to object A. The second argument is the same b, and
Yeah.
t to the minus 1.
Oh, yeah.
So again, use the adjunction, move this f from the first argument to the second argument, so then I'll get t to the minus 1 of A, first argument, and the second argument is the h of B. Right, and to do the same thing with the equivalence again, so I can move it and say that this is home from A to the t applied to the h of B. A very simple string of natural equivalences, and from this I want to say that I can conclude that h commutes with the shift. So why? The question was, well, I have the string of equalities, right? From this,
You had that?
yeah, exactly. So by Uneda, I can see that h prime is natural equivalent to the th. So the right adjoint commutes with the shift. Now we need to show that right adjoint maps distinguished triangle to distinguished triangles. So let's take a distinguished triangle, of course. So ABC. So this is distinguished triangle in the category T. Now if I apply functor H to this, I don't know that I'll get a distinguished triangle, but at least I can do this simple thing. I apply H, say, to the A and B and the map between them, right? So this is a map in the T prime, and I can complete this to a distinguished triangle. So let me just write that I have some object that I'm going to call C0, and then H of A shifted by 1. Right, so this is a distinguished triangle in T prime, which exists by the axiom TR1, right? Okay.
What does
Hmm?
what does
Well, yeah, I'm taking the H of A and H of B and the map between them. And this is kind of diagram in the T prime, and I complete this diagram to distinguish triangle by using axiom TR1.
we just want to prove that C0 is equal to
H of C. Mhm. Okay, so apply the H of A. F is applied to the H of B. F is applied to the C0. F applied to the H of A and shifted by 1. Well, then we have the two maps. Let's say since these two functors are adjoint, we have the co-unit of the adjunction. So in the first column and the second column, then we use axiom TR3 to say that there is a map. Let me call this maybe a psi. And of course there is a map here, which is the shift of the co-unit of the adjunction. When I apply, well, when I take this diagram and apply.
Can we use just like lemon?
Hmm?
Can we use just like lemon?
No,
Why? With no.
because
there is no more reason between.
just a second.
We have some more people from FHA to A, from
Yes.
FHB to.
Well, yeah, but it has to be formulated in a more accurate way.
Because we can we know that there is morphism from third axiom. There is C from F0 to C.
This is just the co-unit of the junction.
Okay.
So, you almost guessed correctly the argument, but it requires a little bit more details. So I want to apply functor h to this diagram, and also on the top I want to add another row. So the next diagram I want to consider is h of a, h of b, c 0. This is a distinguished triangle. Now in the middle, I'll get h, f, this is the map of the h of a, h of b, c. And in the middle, there are h, f, h everywhere. Oh, here we got h, f, c, 0. Okay, now if we look at this map of distinguished triangles from the top and the bottom, right, we definitely know that these compositions coming from the junctions, these are true isomorphisms. Right? We want to conclude from this that this is an isomorphism. Right? So the question is, why would I say just the second rule is wrong? Why I can conclude immediately that this is an isomorphism?
But we know that all of these are, like all of these big compositions are isomorphisms.
No, this is definitely an isomorphism. This is definitely an isomorphism.
Do you want the later?
And I want to say if these are two isomorphisms by what I proved before, then this map is also an isomorphism. So, but this doesn't work in this way, right?
We don't know that the lower row is distinguished.
Yeah, we don't know yet that this triangle is distinguished. That's the problem, right?
This is what we're trying to prove.
We don't know that this triangle is distinguished triangle. But this problem is actually easy to overcome, right? We just use kind of the reduce everything again to the 5 lemma in the category of abelian groups by applying the homological functor. So we can take any object, let's say call this A0 in the triangulate category T, and apply functor home from the A0 blank to the sequence that we have. Well then, well, if you apply this functor to the top row, right, this will be an infinite exact sequence. Now I want to understand what happens when I apply this functor to the bottom row and use the adjunction. So I have home A0 H of B. This is mapped to the home A0 H of C. And this is mapped to the home A0 B, C. Yeah, that's enough. H of A shifted by 1. So by the adjunction, I can say that this is home from the F, which is applied to A0, and object B. And this is by adjunction home from the F of the A0 C. And finally, this is F of the A0 A of 1. So this is of course by the bottom row is exact. So then we can say that the home from the A0 to the C0 is isomorphic to the home of the A0 H of C, right? By applying 5 lemma to the abelian groups. But again, you just use the Ioannidis lemma and see, since this is for any object, that this composition is isomorphism.
How do you imply that home from A0 to C0 is isomorphic?
Oh, because you have kind of this distinguished triangle, you get long exact sequence. Here you also get long exact sequence, but not because this is distinguished triangle, but because this is kind of adjoined to a distinguished triangle. This is the argument here, right? You use the adjunction and you get the sequence, infinite sequence, where, well, actually we only need 5 terms from this sequence, where everything is exact, and the two maps are isomorphisms. So by the Ioannidis, C0 is isomorphic to the H of C. Okay. Okay. So I want to start new section. 1.3. Pullbacks and push-outs. Definition. So I'm going to assume that everything is in 10th grade category. So if I need to square so the maps are F and F prime, G and G prime. So we have a commutative square in the 10th grade category, so it's called homotopy Cartesian. If there is a distinguished triangle of the following form. The map of the object Y is given by the kind of this matrix of the maps G and F. So this is to the direct sum of the Y prime plus Z. And from this direct sum, the map is given by the another matrix F prime, G prime, to this Z prime. Oh, and then there is some kind of additional map down to the Y shifted by 1. So this del sometimes is also called the differential of the homotopy square, or homotopy Cartesian square. So differential. So as you can see that, well, if you work with abelian categories, you have push-outs. Oh, first of all, you have kernels and co-kernels, right? And then you have push-outs and pullbacks. But here, in the homotopy sense, these two notions are the same, right? Because instead of kernel per kernel, what you have is just the home of the map. Or if you rotate, for example, if you start with this part of the diagram, right? You can also extend this to a distinguished triangle by adding something on the left, right? This is sometimes called homotopy fiber of this map. So in the sense that there's only kind of cone, and which is more or less the same as homotopy fiber, there's only a notion of homotopy Cartesian, kind of homotopy pullback and homotopy push-out, they just coincide. And this just means that this data that we have on the square can be reorganized into this distinguished triangle. Well, if you want to kind of keep this terminology, we can say the following. So,
What does the dimension of the conjugate square?
just by definition, well, I construct this, I know that by definition there is this distinguished triangle and there is this additional map. And this map kind of increased the degree by 1, right? So it's just the terminology for this map.
Suppose there should be minus.
Yes, there is a minus. Sorry, I'm minus. Oh, we could put a different place, but because that's here. Yes.
Do we somehow define homotopy limits or classes in the same fashion?
Yes. But the problem is in the translated category, well, it's not an infinity category, it's not a G category, but only defined very limited homotopy limits of very limited diagrams. But we will use them later. But if you have a derived category, then you can define any homotopy limit according to it. And we'll probably also need this later. Okay, so I want to say kind of a remark on just the restatement of this definition is the following, that you can say that in this case, you can call object y, so say y is called homotopy pullback of the diagram where you have y prime mapped to the z prime and z is also mapped to the z, right? So you can keep kind of this part of this standard notation. And you can call, of course, call the z prime, so it's called homotopy push out of the diagrams with y, z, and y prime. So, of course, if you have a homotopy Cartesian square, if you have such a diagram, right? So it means that you have maps only f prime and g prime, right? So you have maps here, and you can complete this to a distinguished triangle. So such y exists, and y that you find you call the homotopy pullback. So of course we didn't prove this, but well, maybe I'll give this as an exercise in the first problem list, that when you complete a map to a triangle, this object is unique up to isomorphism. Or maybe this follows just immediately from the, that's very simple exercise. This follows from what we proved already. So this y is unique up to isomorphism, but this is of course not a functor, right? So in this case, this kind of pullback is not a functor because it's not unique up to unique isomorphism. It's only unique up to isomorphism. So, and for this diagram, you have maps f and g. So you look at this part, you complete this to a distinguished triangle, you get z prime, and z prime is by definition homotopy push out of this data. Okay, so this is just terminology. So a little lemma that we will prove now. For any commutative square, translated category. So let's say this is y and f. So the part of the square is the same as before, g, y prime. But here we have some object p. So for any commutative square with the same 3 objects and 2 maps, there is a map. There is a map from the homotopy push out z prime to the p. So of course, when I have such a map, so such that triangles are commutative. So here we have z Z, it is Z prime, it is mapped to the P, then there is Y prime, there is Z, and there are maps like this. So there are two triangles, and both triangles are commutative.
What's the map from Z prime to Z?
So this is the other direction.
Choose another direction.
Yeah, this is in the other direction, yes. So it's kind of like a universal property of the Z prime, which is the homotopy push out. But the problem, the statement is that there is a map. I cannot say that there is a unique map. So that's the big difference.
That's why it's called homotopy, or there is some deeper meaning behind such terminology.
No, it's called homotopy because essentially the idea is you can present, for example, any limit. You take a product and then you take an equalizer, right? In the triangulated category, well, in the abelian category, equalizer is the same as co-kernel. In the triangulated category, there are no co-kernels. Instead of taking co-kernel, you take the cone. So essentially, when I write this distinguished triangle, I'm saying that I'm kind of replacing the co-kernel of this map by the cone, or by this. If for this map I replace this kernel of this map. If you take the kernel of this map, you'll get the standard definition of the pullback, right? And co-kernel you get push out. But whenever you replace kernels and co-kernels by the cones or homotopy fibers, you kind of get the definition of the homotopy pullbacks and push outs.
Mostly because they're homotopy.
Hmm?
Well, I remember that they are quasi-isomorphic, but I guess it turns out that they're homotopically equivalent. Yes.
What do you mean? This is here.
There
This,
is no notion of.
yeah, this moment is only a triangulated category.
That's just
Well, Y and Z are determined up to isomorphism. If you are in the derived category, this is Y and Z are determined up to quasi-isomorphism.
yeah, I mean, what's going on if we go to chain complex, but I guess we have to discuss it after.
Okay.
Excuse me, you said the triangles are commutative. This means just usual,
Yes, just the commutative diagrams. Yes.
not just DT.
No. This is just as triangle in any category. This is what you require if you have not just a homotopy pullback by a pullback, right? You're supposed to have a map like this, which is in the nice situation just unique. Here we just have an existence such that these two triangles are commutative. Okay, proof. Okay, so I look at the diagram where I have y prime plus z, well, the distinguished triangles that I have before on the top. And I take the distinguished triangle 0, then P, P, and 1, and again 0 shifted by 1, but this is just another 0. Okay, so here, since I have two maps from the y prime and from the z to the p, I have a map defined on the direct sum. Right, so let's call this map phi. It is determined by these two maps. And if you take a composition of this map with the maps, so let's say with the, or if you take a composition of the embedding of the map y to this direct sum and the map phi, you'll get 0. Hence, this is a commutative square. And by one of the axioms, we know that we can find the map here. And commutativity of these two squares is more or less immediately follows from the commutativity of this square. So that's essentially the proof. You can think about the details. Good, so next proposition is kind of a little technical tool that we're going to need later, but this is now the right place to prove this. So suppose we have a diagram. Suppose we have a commutative diagram in which top row is a distinguished triangle. So have a distinguished triangle y by g y prime y double prime. I'm going to call this last by m. So that's a distinguished triangle, and there is also another data. There are two maps f and f prime with the z and z prime, and the map g prime. So the top row is commutative. The top row is a distinguished triangle, and the square is homotopy Cartesian. So then we can actually take this map G prime and complete this to a distinguished triangle. So then there is a distinguished triangle. Where the third object is again y double prime. So there's this distinguished triangle making the diagram with two distinguished triangles. So y g, y prime, y double prime, and y shifted by 1. So here we have z prime, y double prime. So this is f prime. And this last map that makes the diagram commutative is just the identity on the y double prime. And here we have also one notation H for this map and notation L for this one. Okay, so given such diagram, we can complete it to such diagram where this map is just the identity. Okay, so since we are given a homotopy Cartesian square, I have a distinguished triangle that corresponds to this homotopy Cartesian square. So let me just write this distinguished triangle. So this is proof. So the proof, I start with this distinguished triangle y, which is mapped to the sum of the y prime plus c, and the map is matrix G minus f. So first component G, second minus f. So this is the same triangle as before. So, and there is also a split distinguished triangle. We didn't check this, but this is really easy to check that whenever we have triangle where the first map is just the inclusion of a direct summand and the second map is projection to a direct summand, then this is a distinguished triangle. split distinguished triangle. So we have these two distinguished triangles, and if you remember the octahedral axiom that we're going to use for the first time, then the third triangle is supposed to be the composition. Right? So the triangle is determined by this map, this triangle is determined by this map, and also we have G, which is just the composition of the Y, which is mapped to the direct sum. G minus F, and then there is a projection to the Y prime. So of course this composition is just the map. So just a second ago I showed a little bit in the wrong way. So this is the map that I want to consider and complete this two distinguished triangle, and also this is the map that I want to consider and complete this two distinguished triangle. Then the third triangle is the completion of the composition to a distinguished triangle. So this is G. So then I can use the octahedral axiom. So I hope that I can squeeze it here. So Y. So I'm just use the axiom, but I plug in all the right distinguished triangles. So essentially it's just a matter of writing the right maps on the right positions. This is the diagram that you'll get. If I don't have any mistakes. I hope I don't.
With -1 is the third row. When there is 0 minus 1, what is for?
Because this is rotation.
Rotation, yeah.
Yeah, because it's rotation of the.
Mm-hmm.
So
Yeah, but it's not true. There is should be. No. Yeah, just use another octahedral theorem.
well, you can use any formulation that you like, but I use this one.
Mm-hmm.
So then I'll get the.
Then the third column is distinguished.
Third column.
Yeah, and in third column, the last one should be. Oh no. Yeah, the third column to this is distinguished, and that's what we want.
Yeah.
But rotated.
Yeah, but I wanted the distinguished triangle kind of in the first position where I put G, right? And here this is rotated, so I have the distinguished triangle from this, which if I rotate this back, where I have Z, G prime, to the z prime, then map h to the y double prime, and then z shifted by 1. Okay. So that's the distinguished triangle that I promised, right? Still the distinguished triangle that I can write here. And then I need to check that these two squares are commutative. But I claim that you need to look at these two squares here. So for example, we can look at the square with the star and square with a double star. Right, so the square with the star tell us that the h f prime is equal to the k, and the square with the double star tell us that the composition of the f shifted by 1 and m is equal to the L, right? Which is commutativity exactly of this square for the star, and this is double star. So I want to say that this is the end of the proof. Okay, maybe some questions. If there are no questions, I want to.
Is understand true that we use one axiom, fourth axiom triangle,
Yeah, so this is the hydro axiom for the triangles that I have.
and when we carry proof is carry without using triangle.
Well, I don't know such proofs.
Triangle effect. As we know that as we know the hypothesis that actually the fourth axiom doesn't need it.
Well, I'm just saying that I don't know a proof without the hydro axiom. I'm not saying that there is no such proof. Maybe there is, but I just don't know how to do this. Okay, yeah, so the last section in the first chapter, triangulated subcategories. So the last of the basic notions. Definition. So there's two parts. So the first part, let T be a triangulated category. So the full additive replete subcategory.
Can you remind what is replete? Can you remind what does it mean for the subcategory to be replete?
It means that this is closed under isomorphisms. If an object is isomorphic to an object in the subcategory, it can also be a subcategory. So this full additive replete subcategory is called triangulated subcategory. You have a triangulated structure induced from the ambient category. So if or replete just means if you have an object isomorphic to an object in this subcategory, then this object belongs to this subcategory. Maybe I've problem with this one, another object. So if I want to say S in the T is the replete subcategory, this means that if I have X which is isomorphic to y, and y is in S, then x is in S. Quite tautological property. It would be weird not to assume this. Well, actually, there is a notion when you don't require this. I think this is called fragile Jambit subcategory. There are some computations where you get such examples, but probably we won't see this. Okay, so this is full additive Jambit subcategory. If we have two conditions, of course. So first one is that the shift. So for any let me call this a category S. So full additive is this category S is co-generated if for any x in the S, x shifted by 1 is also in the S. So closed up the shifts. And of course 2 is that we have a distinguished triangle. So if for any distinguished triangle in the category T, x, y, z, x shifted by 1, if say x and y are in the subcategory S, then z is in S. So a distinguished triangle, if 2 out of 3 objects are in S, then the third one is also in the S. Okay, this is the first part of the definition, and the second part of the definition that I also want to introduce right away is the notation, well, not really mathematical object, but notation, mod sub S. These are maps. Maybe I just avoid some misunderstandings, write it like this. These are maps in the category T, such that if I complete this map to a distinguished triangle, then the Z is in the subcategory S. This is just a notation. That notation will be important later in the next chapter when it is defined quotient categories. So essentially, when you want to define quotient category, you have two approaches. You can say that you want some objects to be zero in the quotient, right? Or you can say that some maps are isomorphisms in the quotients. So if you take a quotient of the T by S, you can say that every object in the S in the quotient is Q, is isomorphic to 0. Or you can say that any such map is becoming isomorphism in the quotient category. So this is why this is an important notation. Note that this is not morphisms in S, this is just morphisms in tau, but kind of, if you think about S as something that is supposed to be 0, then this is isomorphisms. And that's the idea behind this definition. So first I want to say something trivial, maybe a remark. Every isomorphism is in the more C for any C, right? That is very easy because you can always construct a distinguished triangle where you have x, y, and f, and completed to a distinguished triangle, and of course 0 is in the subcategory S for any S, since S is additive. And this is distinguished triangle, for example, because we have something where you have just the identity, and that distinguished triangles, and triangle isomorphic to a distinguished triangle is distinguished triangle. It's a very easy observation. Yeah, and now I have more interesting observations or proposition. So suppose we have two morphisms, so let f be a map from x to y, and g is a map from y to the y prime. So these are morphisms in the triangulate category T. So if any two of f, g, and the composition gf lie in morphisms S, then so does the third. Again, another 2 out of 3 properties. So the proof is again by octahedral axiom. Just straightforward application of the octahedral axiom. So x, f, y, z, x shifted by 1, identity, x, 0, x shifted by 1, f. So now just writing it one more time octahedral axiom, but I'm now just changing notation. Instead of A, I have X, instead of B, I have Y, but the rest is the same diagram. Maybe this is just an unfortunate choice of the notation in the statement of the proposition. Anyway, so look at this diagram, and then by looking at this diagram, we can say that the f is in the more S. This is equivalent by looking, for example, at the top row, to saying that Z is in the S. Composition G and F is in the more S is equivalent again by the same argument to the fact that the Z prime is in the S. And finally, G is in the more S. This is equivalent to the Y double prime is in the S. But now if we look at this triangle, the last one, so with the Z, Z prime, and Y double prime, for this we know that if the 2 out of 3 objects belong to the S, then the third one belongs to the S. This is definition of the triangulated subcategory. So in the statement, of course, I have X and Y, but because of the rotation, I can say that if any 2 out of 3 is in the S, then the third one is in the S. Hence, this proves this statement. So, proposition. So let's consider homotopy Cartesian square. Notation is as before. Square. So then F is in the mode S, if and only if F prime is in the mode S. And by the symmetry, of course we have the same statement for the G. So G is in the mode S, if and only if G prime is in the mode S. So we're all out of time, and the proof of this is so simple that I want to leave this as another exercise. That's all I want to say. just want to give you an exercise to think about. So you can give a direct proof with tetrahedral axiom, or you can maybe use something that we did before and give a very simple proof of this.